Okay, so we'll start the lecture now. Welcome to live session 2 for week 11 of the course Digital Electronic Circuit, which is taught by Professor Gautam Saha from IIT Kharagpur. And I'll give you a brief introduction of myself. I am Anand Singhal, a PhD scholar from IIT Jodhpur, and I'll be assisting you in solving the previous year assignments problem that will help you in solving the similar problems given in assignment of week 11. So this is the course outline. As we have come to the almost to the end of this course, so I'll brief the course content to you. So in the initial weeks, we know that we have covered the combinational part of circuit till week 6. Then we started the sequential part of circuit, and now in the last two lectures, we are going towards the circuitry part, like using those flip flops or using those combinational circuit. How can we make some application based circuits such as digital to analog converters, which are known as DACs, then different types of analog to digital converters, and some terminology associated to them. So we'll cover these content in this week's lecture. So without further waiting, let's start with the question number one. So question number one states that for a 3-bit weight at register DAC, which is given below, what are the values of R0, R1, and R2 and RL respectively? So I'll give you a brief about what is a 3-bit or what is a binary weight DAC or a digital to analog converter. So it is nothing but a circuit which has a output voltage and some resistors attached to it. So this is how the circuit has been made. So these are the resistances R0, R1, R2, and this R0 represents the LSB. And suppose we are having a 3-bit, so there will be three resistors, and the third resistor will have the MSB. So we will apply the corresponding 1 or 0 here, and there is a finally a load resistor which is RL, which is always grounded. So in general, this RL value is very high as compared to these resistors which are R0. This is approximately three times higher magnitude than this of R0, and the general relation is R0 is the first resistor which is connected to the LSB. Then R1 is nothing but R0 by 2, and it goes on for nth bit. So R2 will be nothing but R0 by 4, and Rn will be nothing but R0 upon 2 to the power n. So this is a basic terminology. So according to the given options, they have asked for R0, R1, and R2, and RL. So RL, we know that it is approximately three times higher than the magnitude. So option A and D will get eliminated directly. And from option A and C, we can see that there is an inverse relation for both the options. So we know that R1 is nothing but R0 by 2. In the options, R0 is given as 100 kilo ohms. So if you try to calculate R1, it will be nothing but 100 by 2, which is 50 kilo ohms, and R2 will be nothing but 50 by 2, which is 25 kilo ohms. So the correct answer to this question will be option number C. Sorry, it is option number B. Okay, since someone has joined, so I'll just repeat in quite the basic of this. Let me wait. So this was a general question for three-way register DAC. Okay, so now we shall proceed to the next question. So the question says if there is a R2R lateral network present in the question, where RF is given as R, the analog output or the output of the circuit is given as 9.37 volts. So it says what is the binary input V3, V2, V1, V0. So we need to calculate these bits of the DAC. So as you can see here is a binary to gray converter attached to the circuit. So whatever input is getting here, let's suppose we are getting V0 dash here, V1 dash here, V2 dash here, and V3 dash here. So whatever output we'll get from the circuit, we need to convert, that will be the gray equivalent. So we need to convert the same to its binary equivalent. Then we'll get the final answer. So don't get confused by the options because it might contain both of the options. So as you can see, it is a R2R ladder network, and the resolution for R2R is given by the reference voltage upon 2 to the power n, where n is the number of bits or number of bit or the n bit DAC. And the general output voltage is given by nothing but resolution into the input voltage. So we'll first check for the full scale voltage, which is for a 4 bit will be 1111, as we know that this is a 4 bit ladder network because there are 4 connections. So 1111 is in binary is 15 in decimal. So we'll write the same. V reference of the circuit is given by 10 volt is given, then 2 power 4, then 2 to the power 3 into 1 that I have already done. It is nothing but 15. So this is 10 by 16 into 15. So once you'll calculate it, this will be uh, 8 by 75 by 8, and it will be 9.37, which is what given in the question. So this is the output voltage which is also given in the question. So we have the input voltage as 1111. So we will not write the answer as that because we know that there is a binary to gray converter attached to it. So we need to convert it into its binary equivalent. So this is the gray code. So for Wien, what we'll do, we'll convert it. So we know that this bit will remain same. Then this bit will get XORed by this bit, so it will be 0. Then this will get XORed by this. This will be 1. Then this will be XORed by the last one. So this will be 0. So this is the binary equivalent. So the answer to this question will be 1010. So once you will attach 1010 here, let me use some different things. 1010 here, you will get 1111 here, which will give a V of 9.37 volt. So the correct answer to this question is 1010, which is option number A. So we'll start the next problem in 2 minutes. Okay, so let's proceed with the next question. So the question says in the below circuit, there are certain values which are given. So we need to find the value of the output voltage. So uh, if the input is this, so input is given as, let's suppose, V in, and there is RF given, there is VRF given, and we need to calculate the output. So this circuit, it is nothing but a DAC 0808. So DAC 0808 is a nothing but a 8-bit uh, digital to analog converter. And for this circuit, there we have a certain formula which is output is given by Vref upon R reference into the MSB divided by 2. So this, since this is a 8 bit, so it will go till 8 by 8, and since 2 to the power 8 is 256, so it will go till 8 256 into R. So we have certain terms. So this is the R, this is RF, and this is VREF, and everything is given in the question. So we'll just apply it. VREF is given as 10 volt, and RF is also given as 10 kilo ohms, and then input is 1, and then last is 1. So first, yeah, we it is nothing but 10 upon 10 kilo ohms into, so this one is 1, which is the MSB, then rest of them are 0, and last bit is 1, and the R is given as 5 kilo ohms. So this kilo and kilo will get cancelled. So this 10 and 10 will also get cancelled. So the answer will be 5 into 1 by 2 plus 1 by 256, which is 5 256, and then 128 plus 2, it is 130. Oh, sorry. This is 128 plus 1, which is 129. So we'll calculate the same. So it is 5 into 129. So it is coming as 2.519. Yeah, 2.519 volts. So the output voltage associated with the given circuit is 2.519 volts. So the correct answer to this option question will be option number D. So you can look through the problem. We'll start the next problem in 2 minutes. Okay, so we'll try to solve a similar problem again with some different values. So you can pause the video during the recording and maybe try it by yourself and then check the solution. So the input here is 111 and then 5 times 0. So this is again a DAC 0808, which is a 8-bit DAC. So the input voltage will write accordingly. So we know the formula is Vref upon Rf, uh, then 1 A1 upon 2 plus A2 upon 4, and so on. Will go till A8 upon 256, into R. So in the given question, Vref is 10, then Rf is 5, and then R is also 5. So Vref is given as 10 volt, Rf is given as 10 kilo ohms, and then Rf is given as 5 kilo ohms, and R is also given as 5 kilo ohms. Let me recheck. Yes. So V naught will be 10 on 5. Then since input is uh, 1, 1, 1, and then rest of them are 0. So A1, A2, and A3 will be 1, and then rest of them are 0. So it will be 1 by 2 plus 1 by 4 plus 1 by 8, and rest of them are 0. And then this is into 5. So 5 kilo and 5 kilo will get cancelled. Finally, we will reach to 1 by 2 plus 1 by 4 plus 1 by 8, which will be 10 into this will have a LCM of 8. 4 plus 2 is 6 plus 1 is 7. This will be 70 by 8, or this will be 4, it's 32. This will be 4 8.375 volts, which is 8.75. I'm sorry. Um, which is option number C. So this is a similar problem, so you can look through the problem again. We'll start the next question in 2 minutes. So we'll proceed with the next question now. This is a general question. So it is given that it is a 16-bit DAC over a full range. So a full scale range is given as 0 to 8 foot, and the input is given as DEC. Sorry, this is C to the base 16. So we'll convert it into its first of all the decimal equivalent. So we know that A, B, C, D, E. So A is nothing but 10, 11, 12, 13, and then 14. So we will have an input which will be D, that is 13 into 16 square, then E is 14 into 16 and then C is 12 into 16 0. So 13 into 256 plus 14 into 16 and then 12 into 1. So we'll do the calculations. So we have 13 into 256. This is 3328 plus, and we have 14 into 16 224 plus 12. So finally we'll have 3564 to the base 10. This is a decimal equivalent. So it is a 16-bit DAC, so the value of n will be 6. We have an input in decimal now, which is 3564 to the base 10, and the full scale voltage is given by 8 volts. So we'll just calculate the output voltage, which is nothing but full scale upon. So this part is the resolution into the input. So we'll calculate the same 8 upon 2 to the power. Uh, this is a 16-bit. Yeah, 16-bit DAC. So we'll write 16 minus 1 into 3564. So we'll do the calculations again. 2 to the power 16 is 65535 to 3564. So this will lead to 3564 65535. So it will come out to a 0.435 volts. So the output for the same will be 0.435 volt, which is option C. You can look through the problem. We'll start the next one in 2 minutes. So we'll start the next problem now. This is a general problem. So it says for a flash bit ADC, which among the following figure denotes the relationship between the number of bits in digital output, which is n, versus the number of comparators. So we know a general relation, which is The number of comparators is dependent upon the number of bits of a flash type ADC. Is a function of the number of bits, and it is given by 2 to the power n minus 1. So this cannot be, figure 3 cannot be the answer since it is independent of n, or it is constant. Then figure 2, we have for 1 we have a certain number which is 1, which is fine, but for 2 we have 3 which is also fine, but if we take, let's suppose, 3, so we have 7 comparators, so it is not 7. And suppose for 4 we should have 15, so it is not 15, so figure 2 is also wrong. Now if we check the same for figure number 1, so we have for 1, let's suppose we need to check for 6, so for n equals to 6 we will have 2 to the power 6 minus 1, which is 65, so it is approximately 65 only. So figure 1 corresponds to the relation between the number of comparators versus the number of bit in flash type ADC. So this will be wrong, this will be wrong, this will be wrong. So the correct answer is option A, and the formula is 2 to the power n minus 1. We'll start the next problem in 2 minutes. Okay, so let's start with a new problem. This is one of the important concept in the in analog to digital converter. So we have few analog to digital converters, and one of the most important is successive approximation type register, which is SAR ADC. So there is a certain method on which this will work. So we'll calculate the same. The question says a 8-bit SAR is used to convert. So the question says that 4.75 volts needs to be converted to its digital output, and the reference voltage is given as 12 volts. The question says the output at the end of third clock pulse. End of it says what it will be. So we'll start with the SAR. So for the 0th pulse, we know we start with all the zeros. That is 2, 3, 4, 5, 6, 7, 8, and this will always be less than the given input voltage. So input voltage is nothing but this 4.75. So since it is less than, so this 0 will always remain. So for the 0 call bus, nothing will change. Now for the first clock pulse, we'll check if the given or the outcoming voltage is getting greater than or not. So we have a 1 0 0 0 and 1 2 3 5 6 7. So we'll check the corresponding decimal equivalent. So first we need to calculate the resolution to calculate the output voltage. So resolution is nothing but V ref upon your n minus 1, so which will be 12 upon, since this is a 8-bit ADC minus 1, so it will be 12 upon 2 to the power 8 is 256 minus 1, so it will come out to be, let's check what it is coming out to be, 0.047 volts. So now we'll check for the first clock pulse. This is binary, so the decimal equivalent is 1 2 3 4 5 6 7 8, so this is 2 to the power 7. So after the first logs, the output will be 2 to the power 7 into 0.047, which is 128 into 0.047. So it is 6.023, sorry, which is greater than the given voltage. So we'll not maintain this one. So this this one will get discarded, and this will get changed to 0, and this will get 1 in the next clock. So I'll write now the for the second clock, it will be 0 1 0 0 0, the same, 2 3 4 5 6 7 8, and the output will be 1047. So it will be half of that, which will be 3.011, which is less than 4.75. So we'll keep this one. So let me mark it. So we'll keep this one and we'll change this to 1 now. And it says at the starting of the third clock. So now we'll check whatever we are getting will be the answer. For third clock, it says at the end or at the starting? At the end. At the ends it says. Okay, so we need to calculate for third also. So it will be 0 1 1 0 0, which will give 64 plus 32. It will be 96 into 0.047, which is 4.512, which is given, what is given, 4.75. So it is still less than 4.75. So we'll also keep this one. So at the end, this one will also get keep it. So the final output at the end of the third will be 0 1 1 0 0 0 0 0, which is given in, yeah, option B. So I'll repeat. So we have a SAR ADC, we have 8-bit SAR ADC, and the given we need to change this 4.75 to a digital output. And the reference voltage given is 12 volt. The question says the output at the end of the third. So end is the main word here, because some question asks at the start, which will be the upcoming question. So initially, for the zero clock pulse, we keep all of them as 0. So there will be no change since the V is greater than the given voltage. Then for the first clock pulse, we'll do this as 1 and we'll keep the rest of them as 0, and we'll calculate the decimal equivalent. So the basic rule is, if this V tag is coming greater than that of V, then we reset the bit, and if this V tag is coming less than V, we keep the bit. So for the first case, it was greater than that of, you can see, for the first case, it was coming greater than. So we have discarded this one, and we have, for the next part, we have not kept this as 1. We have kept the next bit as 1. So for the next bit, the thing was it is less than. So we have kept this one now. And for the third, at the start of the third, end of the third, so we have kept this one. Now if we check for this one, this was also less than. we have also kept this one also. So the final answer after the third clock will be 0110, then 0000, which is option B. So we'll start the next problem in 2 minutes. So we'll start the next question now. So this is again a similar type of question. It says the value of n is 7. So think, and the input voltage which needs to be converted to a digital output is 8.95 volt. The question says the reference voltage is again 10 volts. So we need to calculate the output at the start. So start is the main word here at the fifth clock pulse. So first we'll calculate the resolution. It will be the reference voltage on 2 to the power 7 minus 1, which will come out to be 7 is 127. So let me calculate it. We have 127. So it is 0.0787 volts. So at 0 o'clock, we'll write the same steps again. It will be 00000, since it is a 7 bit, which will be always less than bean, so we'll keep the bit. At first clock, we'll check for 1 and then 1, 2, 3, 4, 5, 6 zeros, which is nothing but 120, 0, 1, 2, 3, 4, 5, 6, 7. Sorry, so 7 is, yeah, 7 is 128. So we'll check the decimal value, which will be 128 into 0.0787, which is 10.07, and this is greater than 8.95. So we'll not keep this bit, and we'll only do this one. So we'll reset it. So now we'll check for after second clock. This will be 0 and then this will be 1. So there will be 7 bits. This will be 64. Let me check I'm doing it correctly. Okay, so this is 7 bit. What I've written here is 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6. So this is 2 to the power 6, not 7. This will be 64. Again, this will be 64. So here it will be, let me reframe. So it will be 5.03, which is less than. So we'll keep this bit. We'll not discard this one. We'll keep this and we'll change this to 1. So for the second log, we have 1, 1, and then this will be 128 plus 64 plus 32, which is 96, and then the resolution. So let me calculate it. It is 7.559, which is less than 8.95. So we'll also keep this bit. This will be 1, this will be 1. So now we'll check for the third clock. So after third clock, we have 1110000. So it will be 96 plus 16, which is 102 then 0.0787. It will be 8.818, which is again less than 8.95. So we'll still keep this bit. Sorry. So we'll keep these as intact. So we'll write now for the fourth one. After fourth, we have 111, then this will be 1. So we have 120 into 0.0787, which will give 9.44, which is greater than 8.9. So this will get reset. This will not be 1, this will get to 0, then this will be 1 at the start of the fifth. So after fifth, we don't need to check for the same, since it says that we need to check it for just at the start of fifth. So this will be start of fifth. So the final answer will be this only, which is 1110100. 111, which is option C. So these types of questions are quite important. So please go through them thoroughly. The final answer is this, at the start of fifth. So we have not calculated what is going at the end, since the question asks at the start. So you need to check whether it is asking for the start or the end. So the previous question asked the same for the end of the third, and this question says at the start of the fifth. So go through it once. We'll start the next question in 2 minutes. let's move to the next question. So the question says the LSB of a, so we have already read about this weight register based DAC. We have already calculated there is a R naught, then this R naught is R naught by 2, R2 will be R naught by 4, and so on, and Rn will be not upon 2 to the power n. So this is nothing but the resolution has been asked, so it is nothing but the full scale minus 1. So it is given that it is a 4 bit, so it will be 2 to the power 4 minus 1, which is 1 by 15. And this weight register works on the principle of KCL. We'll calculate some questions on the basis of KCL in the upcoming questions. So the correct answer to this question is option B. In the next question, we can do it uh, here only. So it is asking for the binary ladder network, which is R2R ladder. So R2R ladder has a resolution we have already covered, 2 to the power n, and it works on the principle of Thevenin or KVL, you can say. So the correct answer is option C. So these are the basics of this 4-bit DAC, binary weight, and R2R ladder network. So these were the theoretical questions. So we'll now do some of the numerical problems of the same. So we can do this problem. So it is given there is a R2R ladder network, and the input is given as 1011, which is in binary. So if we convert it, it will be plus 2 to the power 1, then 0. So it will be 8 plus 2 plus 1, which will be 11 in decimal. So it says what will be the output voltage, and if the V reference is given as 20 volts. We know for the binary, R2R, it is Vref. So this part is the resolution, and then the input voltage. So if we try to calculate, it will be 20 upon 2 to the power 4. Since this is 4 bit, then the input voltage is 11. So it will be 20 into 11 by 16. So it will be 55 by 4, which is 1.3, sorry, this 13 point, then that is 37.5 volts, which is option B. So you can go through it. We'll start the next question in 2 minutes. So let's proceed with the next question. So this question says it is again a 4-bit R2R ladder network. So it says it has an output voltage given of minus 5 volts, and the input is B3, B2, B1, B0, which is 1001, which is in binary. So the decimal equivalent will be, sorry, this is 9. So it is asking for the reference voltage now. So we know in general what is V out. V out is nothing but minus V ref, and then MSB upon 2 plus, this will be, sorry, this will be 4, then this will be 8, then this will be 60. So we know that this is 1 and this is 1 given in the question, and this is 0 and this is 0. So if I try to calculate, it is given V out is minus 5, then minus V ref, so it will be 1 by 2 plus 1 by 16. So if I try some modification, it is V out will be nothing but this minus will get cancelled. This will be 5 into 16 upon, then this will be 8 plus 1, which is 9. So it will be 80 by 9, which is given as 8.89 volt, which is option B. One more method that we can calculate directly is V out. We know it is V ref on 2 to the power n into V in. So we know V in is 9, so we'll directly calculate. Sorry, so we'll directly calculate. Sorry for the glitch. So we'll directly calculate V out is 5, then this V ref, then this is 2 to the power 4 since this is 4 bit, and then V in is 9. So again V ref will come out to be 80 by 9, which is again 8.89 volt. So the correct answer is option number B only. We have a similar. Okay, so this is a good question. So we'll try to do this now. It says the resolution of a any DAC is approximately 0.4% of its full scale range, and we know the resolution is nothing but full scale range upon 2 to the power n minus 1. So according to question, this 1 and 2 are equal. So if it is equal, so let's try to solve it. So full scale range upon 2 to the power n minus 1 will be 0.4%, which is 0.4 by 100 into full scale range. This full scale range will get cancelled, and 2 to the power n minus 1 will be 100 upon 0.4. So if I calculate it, it will be 250, and 2 power n will be 251 approximately, it says. So n will be approximately 8, since 2 to the power 8 is 256. So we have nothing but a 8-bit DAC, which is option 3. This is one of the questions that comes in gate quite frequently, so try to grasp it. So it says that it is 0.4% of full scale range, and we know the resolution is full scale range upon, for a general, it is 2 to the power n minus 1. So we just equate it to calculate the value of n. So we have done that, and we are getting this relation. And according to the relation, we have n equals to 8. So it is a 8-bit converter. So now we'll start the next problem in 2 minutes. So let's proceed with the next problem. So this is again a R2R ladder network only with a external op amp attached to it. So we'll calculate. So it says that we have a certain input which are B4 is 1, then B3 is 1, then B2 is 1, and B1 is also 1. And reference voltage is given as 8 volts. So we'll calculate the same. Let's try with this one. Yeah. So for the given circuit, so there will be a V naught here. V naught is not mentioned in the circuit, so we'll calculate V naught, which will be nothing but minus RF by R, which is the non-inverting gain of this op amp, into the attached voltage, which is nothing but V reference into B1 by 2 plus B2 by 4 plus B3 by 8 plus B4 by 16, and all the bits are given as 1 only. So we'll calculate the same. RF is given as R in the circuit, as you can see. So V naught will be minus R upon R. Then V reference is 8 volts, and it will be 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16. So R will get cancelled, it will be minus 8, then 16 will be the LCM, so it will be 8 plus 4, it is 12, plus 2, it will be 15. So it will be minus 7.5 volts, which is option A. This is a general question, and this is a very easy question. So in general, this topic is quite easy for the DAC and ADC part. So you just need to be good with the fundamentals and with the formulas, whatever you have been taught. The questions will be easier from this topic. So we'll start the next question in 2 minutes, or maybe we can do it right now. So it is asking, it is a general question again. So it is asking for the resolution of a R2 or ladder network. So I've already told you it is nothing but V reference upon 2 to the power n. So V reference in the question, it is given as what is V reference? It is 5 volts, and n is, it is a 8 beta. So if I try to solve it, it will be 5 divided by 2 to the power 8. So it will be 5 divided by 256. So let's try to calculate this same. 5 divided by 2, sorry, 256. So it will be 0.19531 volts. So since all of the options are in millivolts, so it will be 19, sorry, it is 0.09, 0.019531 volts. So it will be 19.531 millivolts, which is option number D. Sorry, it is D. So we'll start the next question in 2 minutes. Let's start with question number next question. So it says in the following circuit, which we have done in the last. So yeah. So it says in the following circuit, what is the output V out when ABCD is 1010. So let's try to solve this. This is again a easier question. It says when this is the input, assume logic 1 has a volt of 2.5 volts. So this is nothing but Vref, that is 2.5 volts, and logic 0 is 0. So what will be the output of the circuit? So it is nothing but V, this is V out. So V out, if there is some current, let's suppose I here, so V out will be nothing but minus I into this RF. So this this is the incoming current and this is virtually ground. So I will be the incoming current from all the nodes. So I will be, let's suppose this is VA. So VA upon R4 plus VB upon R3 plus this VC upon R2 plus, and one more is VD upon R1. And this is 1010. So this is 1, this is 0, this is 1, this is 0. So current will be nothing but 1 upon, sorry, 1 it says it is given by 2.5 volts. So I'm writing 2.5 here now. 2.5 upon R4, R4 is 1 kilo ohms. Then this will be 0, then this will be 2.5 upon R2 will be 4 kilo ohms. And one more it is 0. So I will be nothing but 4 kilo ohms will be the LCM. So 4, this is 12.5. It will be 3.125 milliampere, right? So V out will be nothing but 3.125 milliamperes, and it is V out is minus I into RF. RF was given as 1 kilo ohms. So this was milli. So milli and kilo will get cancelled. So the answer will be minus 3.125 volts, which is option number C. I hope it is clear. This is quite easy and the basic circuit question. We just applied the KCL here. So this voltage will be the all the incoming voltages. So I is VA by R4 plus VB by R3 plus VC by R2 plus VD by R1. And we have substituted the value of 1 which is 2.5 and get the corresponding current. So this current is nothing but 3.125 milliampere. And then this is getting multiplied with this resistance to get the final output, which is coming out to be minus 3.125 volts. So this is also quite a good question, so you need to understand it quite well. Now we'll proceed to the next question. Okay, so let's try the next question. This is quite easy. So it says how many comparators are required for a 3-bit. So for a flash bit, I've already told you about it in the graph. Flash type ADC, number of comparators, and it is a n-bit flash type ADC. Number of comparators are nothing but 2 to the power n minus 1. So for this question, n is given as 3. So 2 to the power 3 minus 1, it will be 7, which is option A. Similarly, for a 4-bit, we will require 15, then for a 5-bit, we will require 31, for a 6-bit, we will require 63, which are the above options. So if n equals to 4 and if n equals to 5, so we can solve it. The formula is 2 to the power n minus 1. So let's try one more question right now only. It is says a sine wave input has a given 7 bits. So it is a 7-bit ADC. And it is asking for the SNR and the worst case SNR. So, and the options are in dB. So due to non-linearity, it is asking. So SNR is given in dB as 6.02 n plus 1.0. What is this? 1.76. So I'm just substituting the value of n, which is 7 here, and then adding the 1.76. So let me try to solve it. So it is 6.02 into 7 and then plus 1 point, sorry, 1.76. So it's come out to be 43.9 dB. And the worst case is given by 6.02 and minus 1 plus 1.76. So we'll just uh, do the same. So we'll just write the SNR minus 6. So it was 43.9 and minus 6 it will be 37.9 dB, which is option number B. So we'll start the next question in 2 minutes. Okay, so let's proceed with the next problem now. So it says it is a single RAM type ADC. So question says it is a RAM type ADC with certain RC and input voltage given. So it says the clock frequency is 1 megahertz. If the ADC generates the digital output after 5 and 2 clock cycles, what is the RAM voltage? So we know that this RAM voltage is given by the slope of this RAM type ADC, which is nothing but Pi upon RC, and it is given as 3.5 millivolt, and R is given as 2 kilo ohms. So I'll try to write this right back, and this is nanofarad. So it is zero point 0.5 into 10 to the power minus 9. So let me try to compute it. So it is 3.5 divided by 2, then divided by zero point 0.5. So it will come out to be 3.5 and then 10 to the minus 6 and then minus 9. So it will come out to a millivolt per microsecond. So you know this is 10 to the power minus 6. So this is microseconds. And the slope is this. So whatever the number of clocks will be, it will get multiplied with the same cycle. So number of clock cycles are given as 512. So the ramp voltage or VR will be number of clock cycles into the slope, which is 3.5 millivolt per microsecond. So this will get multiplied. So let me try to solve it. This is 512 into 3.5. So it will come out to be 1792 millivolts, which is nothing but 1.792 volts, which is given in option D. Let's start. I hope it is clear. This is quite basic. The slope and multiplied with the number of clock cycles. Now we'll proceed to the next question. So it is a basic question again. So it says the output voltage V naught is given by. So we'll apply something. So this is these both resistance are in series. So this will be 2R. So since this is also ground, so let me try to make the circuit. This will be 2R in ground. This will be again 2R in ground. So these both are in parallel. So this will be nothing but R and with a ground. So this R and this R now. This will be in series and the combination will be 2R again. So if I try to make this again, this will be 2R ground and again 2R ground. So this again will be repeated and this will be R and here it will be R to the ground and these two are in series. So if I try to remake the circuit, it will look something like there will be a 2R, then there will be a ground, there will be again a 2R with a certain voltage V connected, then there is a 2R here. So let me try to make the circuit. Uh, so let's suppose this is the on inverting node. So this is this and this is grounded. So this is minus. Now there is a feedback and it says it is R and this is I and this is V out. So we know that if it is ground, so this node is also virtually grounded. So let's suppose the voltage here is nothing but Vx. So I am just applying the KCL. So KCL will be nothing but this will be Vx upon 2R here. Then this will be plus Vx minus V upon 2R. Then this is ground, so this will be Vx upon 2R equals to 0. So let's do some calculations. 2R is the LCM, so it will be 3Vx minus V equals to 0, which will give the V as Vx, sorry, 3Vx. Now this is the current. So we know this is virtually grounded, so current will be nothing but this V out will be nothing but this current into resistance. So V naught, yeah, V out will be nothing but, let me try to solve it. You can see this is Vx, so this is coming out to be here I. So this will be I here also. So it is nothing but Vx minus 0.2R. V out, sorry, I will be nothing but V out, sorry, Vx minus 0 upon 2R, which is nothing but Vx upon 2R. And this will whole be a minus sign since the current is going from high to low. So it will be minus Vx upon 2R and Vx we have already calculated, it is V by 3. And R is not given in the circuit, I guess. So we'll just omit R and we'll write Vx as V by 3 and then this 2 was already present. So it will be minus V by 6R. Since R is not given in the circuit, so we'll just assume the value of R to be 1 according to the options and the answer will be option number C. I hope it is clear. This was quite basic. We'll start the next problem in 2 minutes. Okay, so let's start with the next question now. This is a simple question again. It says it is a 6-bit ladder network. So ladder network we have already read about. Input is given as 101001 in binary. So we'll calculate it is 0 1 2 3 4 5. So this will be 3 plus then this will be 0. So it will be 32 plus 8 plus 1. This will be 41. And it says 1 denotes 10 volts. So VREF will be 10 volts. So the output is nothing for a R2R ladder network. It is this. So we'll just apply the values. It is 2 and it is 6 and then this is 41. So let's calculate the same. This is 410 divided by a 64. It will be 6.40 something. Sorry. So this is a generic ladder network. It is saying. So it is not ladder. It is a weight back according to the question. So we will have this -1 also. And after calculating, we'll get the answer as 6.507 volts, which is option B, 6.51 volts. So let's proceed to the last question for today. So it says it is again a sine wave input and it is a 8-bit DAC, sorry ADC. So it is asking for the SNR for the same NDB. So I've already told you the formula. This is 6.02 n plus 1.76. So it is 6.02 into 8 plus 1.76. So it is 16 and this is 48 plus 1.76. So it will be 2, this will be 789 and this will be 49.92 dB, which is option C. So now I'll just quickly summarize all the questions of what we have done since it was quite a basic topic. So I'll summarize them quickly. So we have started with weight register tag, and we have read about the concept that what are the registers value and corresponding things. And then we have a binary R2R ladder network, and we read about the resolution, which is V reference voltage upon 2 to the power n. And we have read the output voltage is given by the resolution into the input voltage. And we have correspondingly read about the concept of gray to binary also in this question. Then we read about this DAC 0808, which is nothing but a 8-bit DAC, which is a binary weight DAC. So we have a formula V naught is V reference upon R reference into this input voltage and the corresponding resistance given in the circuit. So we have covered the two questions similar with some different values for your good practice. And then we covered a 16-bit DAG with some full scale range. So we have again, this is a generic question. There was some hexadecimal to decimal conversion in this question, and we just calculated the output by the same formulas that we were reading before. Then we covered the comparators for a flash type ADC. It is 2 to the power n minus 1 comparators for a n-bit flash type ADC. So this plot was coming as correct, and rest of the two plots were not giving the same relations. Then this is one of the most important questions for today's lecture. It consists of a SAR ADC, and what we have done is we calculated the output at certain clock pulse. So for the clock pulse, this is the most uh, important concept. This VDAC, if this is greater than Vin, so we need to reset the bit for that particular clock. And if this VDAC is less than Vin, so we'll just keep the bit as 1. So let's suppose for the first clock we have kept this one, for the second we'll take this one, and for second this will be 1, for third this will be 1. So for the first lock, if this given voltage, so it is coming out to be 6.03 for the first lock, and this is greater than the given voltage. So we will reset this bit to 0 and we'll keep the next bit to 1. Now if this is less than, so we'll keep this one intact and we'll change this to 1. So this is the concept. So we have covered two questions with some different values for the same. And then we have done this KVL KCL, sorry, for this weight DAC, it is works on the principle of KCL. And also it has a resolution for n-bit DAC. We have 1 upon 2 to 2 ki power 2 to the power n minus 1. And similarly for the binary ladder, we have a resolution of 1 upon 2 ki power n, and then it is works on the basis of Thevenin theorem. Then we discovered some question of R2R ladder DAC with some input. So again the same formula that we are doing earlier. So input is given by output is given by V reference upon 2 to the power n, which is the resolution, and into the input voltage. Similarly, again a 4-bit R2R ladder network is given, and we have certain input, and this time we were given the output voltage and we need to calculate the V reference. So I told you about the two methods. So this one was the shortcut, not the shortcut, but this one is the easier method, or we should go by the concept. We are getting the same answer as 8.89 volts. Again, this is again an important question. This comes in gate quite frequently. A resolution which is something percentage of full scale range, and resolution is nothing but full scale range upon 2 to the power n minus 1. So we equate both of them to calculate the value of what is the value of n bit. So this is again R2R ladder network, and we have applied the conceptual part, whatever circuit is given. So we have all the inputs as 1 and the V reference is 8. So after putting, we are getting the voltage as minus 7.5 volts. And again the resolution for a 8-bit R2R is given by V reference upon 2 to the power n. this is again a KCL cable question. So we have applied certain concepts of electrical circuit. So this is I is nothing but this voltage which is minus V out into RF. Sorry, V out will be minus I into RF since this is going inside this, and I will be nothing but since this is virtually grounded. So the sum of all these currents. So first current will be VA upon R force, and similarly all these currents. And we have put it the value of given circuit, and one is corresponding to 2.5 volts. So we calculated the corresponding currents multiplied by the corresponding resistance, and we get the final output voltage. Again, comparator, I've already told you this is the formula. SNR, this is the formula, and for the worst case SNR, we'll just remove one bit or we'll do -6. Then for a ramp type ADC, we have calculated the slope and the corresponding clock cycles will get multiplied to get the ramp voltage. Similarly, this output voltage is shown. So we have calculated some circuitry part here also again. So these are in series, then this both will be 2R in parallel with this 2R, and 2R parallel 2R will be nothing but R. And similarly, we reduce the circuit to this circuit, and then we applied KCL at this node. So Vx upon 2R plus Vx minus V upon 2R, and this Vx minus virtually grounded upon 2R will give a relation between V and Vx, and then current will be nothing but this current is the same, so it will be Vx minus 0 upon 2R. So this is what we calculated. So we get the answer as minus V by 6. Then again a simple 6-bit weight DAC is given. So we have NS6 and we calculated the output voltage. So we have done this several times now. And again SNR question. So this is a formula base. So this is how I'll end my lecture today. This was quite short since there were no participants in this. So we'll meet for the next lecture, for the last lecture in the next week, which will cover certain more topics of this course, and then we'll end the session for this particular course. Thank you for attending the session.